Today we are going to discuss the vibrations of rings and arches. In the previous lecture, we initiated some discussions on the dynamics of curved beams, and we had discussed about beams with constant curvature, which are in a plane. So, before we look into the vibrations of rings and arches, let us recapitulate briefly what we discussed in the previous lecture. So, we considered so curved beams are found in various civil structures like bridges. They are used in arches, so and various other places. Now, we looked at the dynamics in the previous lecture on the dynamics of curved beams, and we observed that the important aspect of the dynamics is that the axial and the transverse are coupled. So, they are coupled because of this curvature of the structure of the beam. So, we had made some simplifying assumptions when we discussed about when we formulated the dynamics. We assumed that the beam is still planar, though it is curved in a plane. We considered that we assumed that the deflection is much smaller than the thickness of the beam, and the thickness in turn is smaller, much smaller than the curvature, which was assumed to be a constant. And we also assumed that the Euler-Bernoulli hypothesis holds, which means that a cross section of the beam, which was initially perpendicular to the neutral fiber, remains perpendicular to the neutral fiber, remains flat and perpendicular to the neutral fiber even after deflection. So, we neglected shear, which means that we considered that the beam is infinitely stiff in shear. So, with such considerations, in the previous lecture we have derived the equation of motion using the variational formulation. So, we considered the Lagrangian, which we wrote as the kinetic energy minus the potential energy, and the kinetic energy was 1/2 of rho a here. These are the field variables. So, u so this is the field variable for the axial or circumferential motion deflection, and this is the transverse W is for the transverse deflection. So, this and minus the potential energy we calculated as so here the angle varies from say 0 to whatever angle you have. So, the angular extent of the beam. Now, in the previous lecture we also made a simplification based on certain redefinitions. So, let us consider some non dimensionalization So, the time is non dimensionalized So, t tilde is the non dimensional time, u is non dimensionalized using the radius of curvature of the beam. Similarly, w was non dimensionalized. Now, using this non dimensionalization, we can rewrite this Lagrangian So, this is our Lagrangian. Here SR we had defined as the slenderness ratio, which So, this is the slenderness ratio, which tells us how slender the beam is. So, higher the value, the more slender it is. So, it is the radius of curvature divided by the radius of gyration of the cross section about the neutral axis. Now, so with this Lagrangian, we derived the equation of motion. So, this was the equation corresponding to u, the circumferential motion, and corresponding to the transverse motion we have these two equations. So, today we are going to first discuss the vibrations of rings. So, in the case of the equation, the two equations of motion. So, this is the for the circumferential motion, and this is the radial or the transverse motion. So, we imagine that we have a uniform ring So, this is the radial direction, and this is the circumferential or tangential direction. This is the angle theta. Now, the boundary conditions, we discussed the boundary conditions for a complete ring like this. So, it turns out to be periodicity conditions. On the field variables. So, we have the periodicity conditions on the field variables. Now, we are going to perform the modal analysis of this system. So, we search for solutions with the structure So, we are interested in solutions with this separable structure. Now, you see that this is a function of theta and t. Now, it must be periodic in theta. So, we must have solutions of the form like this. So, where n can take values 0, 1, 2, etc. So, this is to enforce the periodicity conditions, to satisfy the periodicity conditions that we have written here. So, we search for solutions of this form. Now, here, so if n is 0, then as you can see that it becomes independent of theta, which means then we are talking about axisymmetric modes. So, modes which are independent of theta. For non-zero values of n, we have non-axisymmetric modes. So, let us see what happens when we consider a solution like this. So, we substitute this solution in the equations of motion. So, if you do that, then it can check that upon simplification of these equations, so this is the first equation. The second equation reads So, these are the two equations that we obtain by substituting the solution form, modal solution form in the equations of motion. Now, for non-trivial solutions of u and w, this capital U and capital W, we must have the determinant of this matrix. So, we can write this as a matrix So, determinant of m must vanish. So, for non-trivial solutions of u and w, and that leads us to the characteristic equation, which can be obtained easily. So, this is our characteristic equation. Now, we have to solve for omega from this equation, substitute in these two equations and then solve for these eigenvectors u and w, and then we will obtain the eigen functions So, you see the eigenfunctions will be complex like this. So, u and w themselves will be can be complex, because you have this I here in these equations. So, u and w are themselves complex, and hence these eigenfunctions are all complex. Now, we have discussed already that when you have complex eigenfunctions, we both the real and the imaginary parts of this can be the eigenfunctions, and so what we can conclude is that for a given eigen frequency we can have more than one eigenfunction. This is called degeneracy. So, we have we have multiple eigen functions for a given eigen frequency. Now, let us see then solve this equation, characteristic equation, and try to find out the eigen frequencies and the eigen functions which will characterize the mode of vibration. So, we start with the value n equal to 0. So, let us consider axisymmetric . So, n is equal to 0. So, if n is equal to 0, then you can see straight from here so from here, so n being 0, so this is the characteristic equation for axisymmetric modes. So, that would imply so you have omega equal to 0 and omega equal to plus or minus 1. So, let us first look at omega equal to 0. So, the eigen vector corresponding to omega equal to 0 turns out to be, if you solve the matrix equation, then u and w turn out to be 1 and 0. Now, this means that, see, the solution was so n is 0, omega is also 0. So, this term is absent, and so the motion is, this is 1 and this is 0. So, which means there is it is a motion along the circumferential direction of the ring. With 0 frequency. So, this is nothing but a rigid body mode. So, this is a rigid body mode, which implies that angular momentum is conserved. So, this is not a vibratory mode. So, next let us look at the other solution, which is omega equal to plus or minus 1. So, in this case, if you solve the eigenvector, that turns out to be 0 and 1. So, now there is no motion in the circumferential direction, the motion is. So, here n is equals to 0, but omega is plus or minus 1, which means it is an oscillatory mode. So, it will be an oscillatory mode, which is only in the radial direction. So, you have something known as a breathing mode. This is sometimes known as a breathing mode. So, the ring expands and contracts axisymmetrically. So, this is a breathing mode. So, this shows this the breathing mode. Now, next let us consider the case n equal to 1. So, now we are talking about non-axisymmetric modes, of course, because there is theta dependence. As soon as n is non-zero, we have theta dependence. So, in that case, if you substitute n equal to 1 in the characteristic equation, once again you will find that the first solution is omega equal to 0. So, this is one solution for n equal to 1, omega equal to 0 is again a solution. So, that you can see directly from here once again. So, if n is equal to 1, so this term drops out in the characteristic equation. So, once again omega equal to 0 is a solution, and then there is another solution which can be determined from here. So, the first solution is omega equal to 0. Again we suspect that this is a rigid body mode, which it is. So, if you calculate once again the eigen vectors, they turn out to be I and 1. So, let us see what this means. So, this gets multiplied, the eigen functions are nothing but so these are the eigen functions. And that can be written as so, if you consider this this solution, then let us see how is the deformation. So, this is the ring. So, now, so this is the deflection of the center the neutral fiber. Now, sin theta with a negative. So, this implies that so this is the theta equal to 0, this is the datum. So, this is u, this is the u motion and this is the w motion. So, u is 0 here, whereas w is plus 1, and then you will find that at this point theta equal to pi by 2. So, this is minus 1. Now, minus 1 would mean, because the axis here is like this, so minus 1 would mean this, and similarly you can find out that this represents a motion like this, and similarly this eigen function vector will represent a motion like this. So, these are nothing but the rigid body modes in the x direction and in the y direction. So, these are again rigid body modes which imply linear momentum conservation. Now, let us consider the other solution. For n equal to 1, we saw that there are two solutions, one was 0, the other one turns out to be this, and the eigen so for this the eigen vectors happen to be given by this complex notation. So, this turns out to be following this notation. So, if you multiply this with exponential I theta, so here we have so these are the eigen function vectors. Now, here now in every so these are actually the non-dimensional frequencies. If you want to find out the dimensional frequencies, they are given by So, these are the dimensional frequencies. So, these are the eigen functions that we have for this mode. Now, let us have a look at this mode. So, this shows the mode because of some aspect ratio problem. It might seem a little like an ellipse, but actually this dashed one is actually a circle, which is the undeformed position of the ring. Now, here you and this black one shows the mode corresponding to the imaginary part, as you can see here. So, let us understand this motion before we look at this picture again. So, let us consider this imaginary part. So, once again let me draw the ring. So, if you consider this imaginary part of the solution, so this as the eigen function. So, the motion can be written as where omega is of course given by this eigen frequency, circular eigen frequency. Now, so in the circumferential direction you have this as sin theta. So, which means here there is no circumferential motion, but there is this radial motion. Here you have circumferential motion as you increase. So, you have circumferential motion here, the circumferential motion is the maximum, which is positive plus 1. So, in this direction, and when you come here this motion is purely radial, there is no circumferential motion at this point. Similarly, you have circumferential motion in the negative direction here at this point and no radial motion here. So, which means that you expect the ring to so the center line of the ring will look like this. It seems that the center, that at least the geometric center of the figure has shifted. I mean, this is an exaggerated figure of course. It seems that the geometric center has shifted, but actually the center of gravity of the ring is not shifting because of a combination of radial and circumferential motion. So, the particles are actually moving in this direction circumferentially, while radial motion is like this. So, we will look at this figure once again now. So, here you can see this is the undeformed ring, and I have drawn these empty circles to indicate the particles before deformation, and these filled circles are these particles after, or these material points after deformation. So, you can see that there is a clustering of these material points here. So, you have compression here and rarefaction here, so that finally it is a momentum conserved mode. So, continuing this way you can then solve for higher modes, but then let us see something interesting. Now, we have discussed as yet till now this mode, which was the breathing mode, and this mode, but they are not the lowest modes. The lowest mode appears to be like this. Once again there is some aspect ratio problem. So, this dashed one is the undeformed ring, and this is the deformed configuration. So, you see this this in this mode it is moving out here and moving in here, and vice versa. So, this is going to oscillate like this, and so there is a phase difference of between this and this which is pi. Here you have the higher mode. So, you can see the circular eigenfrequency non-dimensional. This is the next higher, and this is the fourth mode, and this is the fifth mode, and so on. So, you can calculate all the eigen frequencies of various modes and also plot the eigen functions. Now, looking at these figures, it might seem that these are nodal points, but this has to be checked properly, because now we have not only radial motion, but also circumferential motion. So, if a node is considered to be a point at which there is no motion, then this might not be a node. For example, here this is definitely not a node. So, occurrence of actual nodes has to be checked by looking at motion of material points on the ring. So, till now we have been discussing about vibrations of rings. Next we will discuss vibrations of arches. So, circular arches. So, a circular arch is nothing but a sector of a ring. We will consider two examples of arches. One is the pinned arch and clamped. Now, as you will realize that the equations of motion for the arches for the curved beams, they are coupled and complicated. So, what we are going to do for the case of arches is that we are going to solve this approximately using the Ritz procedure. So, let us see what are the boundary conditions, because we need to choose admissible functions for application in the Ritz method. So, let us look at first the pinned arch. So, this is a schematic representation of a pinned semicircular arch. Now, the boundary conditions if you look back on the discussions we had on the boundary conditions of the curved beams, then at theta equal to 0 and theta equal to pi, we must have u equal to 0, which is the circumferential motion, and w equal to 0, and we also must have so we have 6 boundary conditions as we had discussed. So, here we have 0 displacement at these 2 points, and this is the 0 moment condition at these 2 ends. Now, so we have these as the geometric boundary conditions. So, to choose now we have to choose admissible functions. So, we can choose admissible functions. So, we expand our field variables. So, the way I have chosen for this problem, so the first admissible function, so this is 0 at theta equal to 0 and also 0 at theta equal to pi. So, I can now construct so I have taken a 3 term expansion for u, and similarly a 3 term expansion for w using the same admissible functions. Now, these expansions we substitute in the Lagrangian. So, we have a semicircular arch, so 0 to pi, so this is our Lagrangian. So, we substitute these expansions here and do the integration over theta, and finally, we obtain the discretized equation of motion in terms of these coordinates a. So, we will obtain where these vector a is a1 to a6, and we can perform the modal analysis and obtain the circular eigenfrequencies. So, for this arch pinned arch, the non dimensional circular the first two non-dimensional circular eigen frequencies are obtained as. Now, from here you can calculate the dimensional circular eigen frequency. Now, this figure shows the first two modes of vibration of the pinned arch. So, you can see that so this is the unsymmetric mode and this is the symmetric vibration mode, which is having a higher frequency. Now, in a similar manner you can perform for a clamped arch. So, this is a clamped arch. Here the boundary conditions at zero and pi happen to be like this. Now, here all the boundary conditions are geometric boundary conditions. So, in view of this, we have this expansion Now, here because you have this slope condition as well. So, del w del theta condition. So, the admissible functions for w must be taken like this. So, theta square pi minus theta whole square. So, if you once again substitute this in the expansion and calculate the discretized equation of motion and further calculate the eigen frequencies, they turn out to be. So, the non-dimensional circular eigen frequencies appear as so, these are higher than the pinned case as we expect. So, here this figure shows the modes of vibration. Again, this first mode is the unsymmetric mode and this is the symmetric mode with higher frequency. So, let us recapitulate what we have discussed today. We discussed the vibrations of rings and arches. So, we have looked at some interesting results in the vibrations of rings and we have considered two kinds of semicircular arches, and using Ritz's method we have determined the eigen frequencies and modes of vibrations. So, with that I conclude this lecture.